Hi everybody, we're going to introduce the next stage in understanding fluids, and that's hydrodynamics. Hydrodynamics, the key word there is dynamics, in that we're going to look at fluid flow. So the previous aspect with Archimedes' principle, Pascal's principle, was all about static, pressure, density with fluids. Now we're going to look at what happens when you flow. We're going to base this on some fundamental assumptions. I'm not going to address them right here. That'll come up a little bit down the road. What we want to get into are addressing two major principles that go along with fluid flow. One is the law of continuity, and then we're going to use that and couple that with Bernoulli's equation, or Bernoulli's law, to understand how the velocity, pressure changes when you have fluids flowing generally in a pipe system. So let's start off with what might look like a strange little illustration here. So we have a pipe that constricts right here, and the fluid is flowing with a certain velocity, and one of the assumptions is we're going to neglect drag forces and even something called viscous forces, which will come up later. And what we have here is if you will, a disk of area, right? We have a cross-sectional area here, and in a certain time the fluid flows some arbitrary distance, delta L. There is a pressure, an external pressure that is felt there that is driving the fluid. Okay, and then we can look at another area here where we're at the same area. Nothing's really changed about the pipe except that the fluid has moved from this section is moved to that section. We're still at the same pressure, P'1. And then we want to understand what happens to the fluid when it goes into the constricted part where we have an area that is, in this case, smaller than the original area. We're going to look at what happens to the velocity, if anything at all, what happens to the pressure felt, if anything at all. Okay, so let's reintroduce something we learned last year especially around rockets momentum, and that's flow rate. And we're going to look at two different aspects of flow rate: mass flow rate and volume flow rate. They're directly related. So mass flow rate, if you recall from last year's m dot, is how we usually signify it, and that's by definition the rate of change of mass as it's moving. So mass is a density of the fluid times a particular volume divided by time. And if we look at this little, like I said, disk of water, a section of water that's moved in a certain time, we can understand that volume of this thing is really just a cylinder. So that's the rho of the fluid, and the volume is an area times this height, which in this case is the length that it moved in a particular time. Okay, so what does that lead us? Well, the distance divided by time here is nothing more than velocity. So a convenient way of measuring mass flow rate is the density of the fluid multiplied by the area of the pipe multiplied by how fast it is moving. Okay, so sorry, I got distorted there. Volume flow rate follows by the same example, right? By definition, I'll call that a big V dot. That's the rate of change of volume. Well, if volume and mass are related by density, right? Density is mass divided by volume. It would follow that the volume flow rate is nothing more than mass flow rate with the density taken out. In other words, volume flow rate is the cross-sectional area times the velocity. So that's really convenient to know, especially volume flow rate, because we usually focus on that a little bit more than the mass flow rate. So this leads to the first important principle of moving fluids, and that's the law of continuity. And it's one of the few laws that we're in chapter that's not named after somebody, because we have Pascal, we have Archimedes, and we're going to learn Bernoulli. It would be nice to attach a name to this, but oh well. So it's a very simple law. In a closed system, that means fluids aren't entering or leaving our system. The flow rate, whether it's volume or mass, is the same everywhere. Okay? And that is nothing more than the law of conservation of mass. It's basically saying the amount of water or fluid that enters one region must be the same as the other in terms of the flow rate. Otherwise, you would be losing mass, so to speak. So that has an important implication in that if the volume flow rate for up here has to be the same as down here, yet this part is constricted, how do you make up for that? Well, if it's constricted, to get the same volume, we've got to cover a greater distance in a particular time. In other words, the fluid must pick up speed. Okay, so sections of large diameter or area correspond to lower velocity and vice versa. So that's really important, and that's what the schematic helps us see. So again, take a look. If I want to represent a certain volume, here I have a big area times a small height, if you will, or length. So to keep that constant, if I constrict to a smaller area, I have to have a greater length in that time, and that means we're flowing faster. So the law of continuity can be expressed as such. For any given section, A1 times V1, right, that's your volume flow rate, has to equal A2 times V2. I could just as well put a rho in there for mass flow rate, but that's going to cancel out because the density, we're assuming the density of the fluid is staying the same everywhere. So that leads to that. So very often, if I want to know the velocity in some part, it's just a ratio of the areas, okay? So that's a law of conservation of mass. So you'll see that again and again, and that's again when we constrict or change the area of a pipe. So there's a simple little example. We have a cross-sectional area already given rather than diameter, but sometimes diameter will be given, so you have to do the pi r squared stuff. Flowing at a rate of 5 meters per second, so the units tells us that's V, as opposed to m dot. What is the mass flow rate? What is the volume flow rate? Okay, so that's right now, that's fairly trivial, but again, just to remind us, so m dot is rho. I don't know why this thing's so distorted. I'm going to pause it. Okay, let's see if that's any better. So m dot is going to be rho AV. Rho, hopefully by now you understand that's water, or this is water, 100,000 kilograms per meter cubed, times the area, times the velocity. I'll spare plugging that all in, but if we plug in the numbers, we've got 155 kilograms per second. Okay, so that's quite a high flow rate. And then if I want to get the volume flow rate, V dot, all I do is take the mass flow rate and divide it by the density, or in other words, just A1 V1. But it's 155 divided by 1,000, that's the density, so we're going to get 0.155 meters cubed, that's volume, per second. Okay, pretty straightforward. Downstream, the pipe constricts to half the diameter. Okay, what is the volume flow rate going to be? So we've got to be careful here, because the tendency is to say, okay, if we've changed the diameter, we're going to somehow change the flow rate, but it's not. The flow rate is the same. That's the law of continuity. But the speed will change, and so we know that our new speed, I'll call it V2, like I said before, is the ratio of the V1 times the ratio of the areas. In this case, the areas are going to be proportional to R2 squared over R1 squared. So since we have half the diameter, okay, let me make sure I got that right. Nope, I got my subscripts mixed up. Silly me. R1 squared over R2 squared. So it's half the diameter, so it's going to be 1/2. No, not 1/2. 1 over 1/2 quantity squared times V1, or 4 times the velocity. And then we could also ask a more, not necessarily a related problem to the constriction, but let's say we want to fill up a pool. We have a hose or something like that. So if we have that and the radius is that, how much time will it take to fill it up? Okay, and the idea here is if volume flow rate, because we have that information somewhere, right there, is by definition the rate at which volume changes, then we can say that the time it takes is going to be equal to the volume. In this case, it's going to be pi r squared of that particular pool divided by the rate at which we are filling it up. And I don't know if I've solved this. Yeah, I have solved it. I think I did it correctly. Anyway, if I do the volume, it's let me put in numbers, 3.53 meters cubed over 0.155 from above, and we get 22.8 seconds, which seems to me rather low. So a 1/2 meter, 1.5 meters in diameter, filling up that fast, that's a really high flow rate. So perhaps the values here aren't realistic, but that's not the issue. Okay, so I'm going to stop here, and then I'm going to, because I got only 5 minutes left, and I want to be able to take my time with Bernoulli. So I'm just going to do a separate video that introduces Bernoulli, which is going to look at flow rate, where we change height, and it's really all about conservation of energy.